In this lecture, we discussed the power of a point with respect to a circle. We take a circle C sub 1 centered at O and an arbitrary point P on the plane. For the most part of this lecture, we take the point P to be outside the circle. The discussion for the case when P is inside the circle is very similar to the case when P is outside. The case when P is on the circle is an easy variation of the situation that is shown on the screen. From the point P, we construct a segment that intersects the circle at a point A sub 1, extend the segment further to intersect the circle a second time at a point A sub 2. An easy variation to the problem is the case when A sub 1 and A sub 2 coincide, so that instead of a secant line, we have a tangent line to the circle through P. One can easily argue that the situation of a tangent line through P is a special case for the situation that we present here. The power of the point P then, with respect to the circle C sub 1, is equal to the distance of P to A sub 1 times the distance of P to A sub 2. We will derive a formula for this product and show that it is independent of A sub 1 and A sub 2. We construct another segment through P intersecting the circle at the point P sub 1, extend the segment further to intersect the circle at another point P sub 2. We construct two additional chords, chord A1B2 and chord A2B1. We now make the following claim. We claim that triangle A1PB2 is similar to triangle B1PA2. As a consequence, in terms of corresponding parts of similar triangles, using the short sides, PA1 divided by PB1 equals PB2 divided by PA2 using the long sides. And if we cross multiply, we get PA1 times PA2 equals PB1 times PB2. Observe that this product on the left is what we had defined earlier as the power of the point P with respect to C sub 1. But what the right side of the equation also says is that we can use any other secant line to define the power of the point P with respect to C sub 1. And so the implication is that the power of a point with respect to a circle depends only on the point and the circle. The current definition of the power of the point also allows for the possibility that P is on the circle, so that P is equal to A sub 1 and B sub 1, in which case PA sub 1 and PB sub 1 are both equal to 0, so that the power of the point P is equal to 0. We would have gotten this same equation had P been inside the circle. The argument would almost exactly be the same as for the case when P was outside the circle. We leave that as an exercise for the viewer. Let us proceed with the proof of the claim that triangle A1PB2 is similar to triangle B1PA2 for the case when P is outside the circle. We go about the proof by showing that corresponding angles between the two triangles are congruent. And we only need to show two pairs of congruent corresponding angles. The first pair of congruent corresponding angles is really just one angle, and that is the angle at P. Angle P, of course, is congruent to itself by reflexivity. For the next pair of angles, we claim that this angle at B2, angle A1B2P, is congruent to this angle at A2, angle B1A2P. Here's the explanation for why they are congruent. Both are inscribed angles in the circle. At the same time, they intercept the same arc A1B1 of the circle. It is a well-known fact that inscribed angles of a circle that intercept the same arc have the same measure, and are therefore congruent. Therefore, by AA similarity, triangle A sub 1P B2 is similar to triangle B1P A2. And it follows that PA1 times PA2 is a constant that depends only on the point P and C sub 1. This begs the question, what is the value of this constant? To determine this constant, let us isolate the secant line through PA1A2. Let us suppose that the points A1 and A2 start sliding towards each other along the circle, so that they converge towards a single point. So that the secant line is now the tangent line through P, tangent to the circle at the point T. The distance PA1 tends to PT, as does PA sub 2. And so when this happens, the power of P with respect to C sub 1 tends to PT squared. But the power of P is a constant, and the limit of a constant is the constant itself. And so the power of P, or PA1 times PA2, is equal to PT squared. And since line PT is tangent to the circle at T, the radius OT should be perpendicular to the tangent line. So that segment OP serves as the hypotenuse for the right triangle OTP, and PT squared equals OP squared minus OT squared, or the power of P with respect to C sub 1 is equal to the square of the distance between O and P minus the square of the radius of the circle.